Welcome to the deep dive. We've got
Yeah.
some listener questions about this holographic principle thing,
Oh, yeah.
and it sounds kind of out there, I have to admit.
Definitely a little mind-bending.
Yeah, so we're going to deep dive into it, and hopefully at the end of this we can kind of break it down into something that makes sense.
Exactly.
So from what I understand, it's saying that our three-dimensional world might actually be like a projection from a two-dimensional surface.
Yeah, like a hologram.
Yeah, like a hologram. And that's a lot to unpack.
Yeah. Where do we even begin?
Right. So maybe we should start with like the basics.
Yeah, for sure.
Like, how did this idea even come about?
Well, it kind of all goes back to this problem in physics back in the early 1900s
Okay.
called the ultraviolet catastrophe.
Ultraviolet catastrophe. That sounds pretty dramatic.
Yeah, it was a big deal at the time.
What was that all about?
Okay, so imagine a light bulb,
All right.
like a regular old light bulb.
I got it.
Physicists back then were trying to figure out how it emits light and heat, right?
Sure.
According to classical physics, the light bulb should be emitting like an infinite amount of ultraviolet light.
Infinite.
Yeah.
Infinite.
Okay, well, that's obviously not happening because otherwise, like every time we turn on a light bulb,
We'd all be fried.
yeah, we'd be in trouble. So something wasn't adding up.
Exactly. It was a huge discrepancy between theory and observation.
So what did they do about it?
Well, this physicist named Max Planck,
Okay,
he came up with this revolutionary idea.
okay.
He proposed that energy isn't emitted continuously like a stream of water, but in like these little discrete packets.
It's like little bundles of energy.
Exactly. And he called these packets quanta.
Quanta. So that's where we get quantum mechanics from.
Precisely. Planck's discovery basically gave birth to the whole field of quantum mechanics.
Wow, so a light bulb problem led to like this huge revolution in physics.
It did.
That's incredible.
And you know what this has to do with the holographic principle?
I don't. Actually, tell me. Well, it suggests that information which is closely related to energy might also be quantized.
Okay, so we've gone from light bulbs to quantum mechanics to information.
That's right.
Where do black holes fit into all of this? Because it seems like they're always involved when we talk about the weirdest parts of physics.
You're telling me black holes are like the ultimate cosmic laboratories.
So how do they connect to this whole holographic idea?
Okay, so first of all, we got to remember that black holes are super dense objects.
Like unbelievably dense.
Right, with gravity so strong that nothing, not even light, can escape them.
Once you cross that event horizon,
Exactly.
you're gone.
So that's interesting, but how does that relate to the holographic principle?
Well, classically, black holes should have zero temperature.
Because nothing can escape.
Right. But their behavior suggests that they actually do have a temperature.
But if nothing can escape, how can it have a temperature? It seems like a contradiction.
It does. This led to the development of this concept called black hole entropy.
Entropy. Yeah, it's basically a measure of disorder or randomness.
Okay, so like a messy room has more entropy than a tidy one.
Exactly.
Okay, I get it.
And what Stephen Hawking showed was that black holes have this enormous entropy.
Really?
Yeah, and it's proportional to the area of their event horizon.
That's interesting. So you're saying that a black hole's information content is linked to its surface area and not its volume.
Exactly.
That's kind of like saying that the contents of a whole library can be written on its walls.
It is, and that's precisely where the idea of the holographic principle comes in.
It takes that concept and applies it to the whole universe.
Exactly. It's like saying that the maximum amount of information that any region of space can hold is proportional to the area of its boundary, not its volume.
Okay, now that is mind-bending. So are you saying that we're living in some kind of giant cosmic projection?
It's a wild idea, right?
Yeah.
But keep in mind, we're talking about information here, not the actual physical objects themselves.
So it's like how a two-dimensional hologram on a credit card can encode a three-dimensional image.
Yeah, that's a good analogy.
Okay, so the information about our three-dimensional reality is stored on a two-dimensional surface, like a giant cosmic hard drive.
You got it. That two-dimensional surface is often called the holographic screen.
Holographic screen, okay.
But to really understand how this could work, we need to dive into a couple of other pretty mind-bending ideas.
Oh boy, bring on the mind-bending. What other concepts do we need to wrap our heads around?
Well, there's these two key principles that support this whole holographic idea. They're called unitarity and black hole complementarity.
Unitarity and black hole complementarity. Those sound like a mouthful.
I know, right? But they're actually pretty simple concepts once you break them down.
Okay, so break them down for me. What do they mean?
All right, so let's start with unitarity.
Okay.
This is the idea that information cannot be destroyed in a closed system like the universe.
So even if something falls into a black hole
Right.
and disappears from our view,
Its information still exists somewhere.
so it's like saying that even if you shred a document, the information it contained isn't really gone.
Yeah, it's just scrambled beyond recognition.
Okay, I like that analogy.
Good.
So that's unitarity. What about black hole complementarity?
That one's even more mind-blowing. It basically says that information can be both inside and outside a black hole simultaneously.
Wait, hold on. How is that even possible? It's like saying you can be in two places at once.
It's all about perspective. From the point of view of someone outside the black hole, the information is encoded on the event horizon.
That boundary of no return.
Right. But for someone falling into the black hole, the information appears to be inside.
Whoa. Okay, so it's all relative. My brain is starting to hurt.
I know, right?
Yeah.
But these ideas, unitarity and black hole complementarity, they're super important for supporting the holographic principle.
Okay, I'm starting to see how it all connects now.
Yeah.
But I've also heard that string theory has something to say about the holographic principle.
Oh yeah, string theory definitely plays a role here.
So what's the connection?
Well, string theory suggests that there might be more dimensions than the 3 spatial dimensions we experience.
More dimensions, like beyond length, width, and height.
Exactly.
Huh.
It proposes that our universe could be like a membrane or a brain for short floating in this higher dimensional space.
So like our universe is a slice of bread in a cosmic loaf.
Yeah, something like that.
Ugh.
And according to string theory, this holographic screen where all the information about our universe is encoded could exist in one of these extra dimensions.
Okay, so I think I'm starting to get the big picture here.
Good.
But it still raises a lot of questions.
Of course.
Like if our three-dimensional reality is just a projection from a two-dimensional surface, what does that mean for us? Are we just shadows? Are we even real?
Whoa, 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 hold on. Let's not get too carried away. Remember, this is all theoretical physics.
Right.
We're still trying to figure out what it all means.
Okay, so I'm getting a little ahead of myself,
Yeah.
but it's hard not to when we're talking about such mind-blowing stuff. So where do we go from here? What's the next step in exploring this whole holographic universe idea?
Well, to really make sense of all this, we need to look at what this holographic screen might be like
All right.
and how it could possibly encode information about our universe.
Okay.
And for that, we need to dive into some of the potential theories that try to describe these holographic screens.
Sounds like we're going even deeper down the rabbit hole.
We are.
I can't wait. Let's
jump right in.
yeah, let's do it.
All right. Okay, so where were we? Oh, yeah, holographic screens.
Right, holographic screens. It's like the universe's biggest movie screen.
Yeah, kind of. But instead of projecting images, it's projecting reality itself.
Okay, so how do we even begin to understand what this screen might be like?
Well, one way is to look at this theoretical space called anti-de Sitter space.
Anti-de Sitter space. Now that's a mouthful.
It is a bit of a tongue twister, but it's a really cool concept.
So what's so special about this anti-de Sitter space?
Think of it as like a simplified model of space-time with a very specific geometry that makes it easier to study.
Got it.
Now, what's interesting is that in some theories, everything happening inside this anti-de Sitter space,
Everything.
yeah, like all the physics and all the information can be completely described by information on its boundary.
On its boundary.
Yeah.
So it's like a perfect example of this holographic idea.
Exactly. What happens inside is mirrored on the surface.
Okay, so if this anti-de Sitter space is like a holographic toy model,
You could say that.
could there be similar holographic theories that describe our own universe?
That's the million-dollar question.
But how would such a theory even work? I mean, our universe is so vast and complex.
Yeah, it's definitely a challenge.
How could you possibly describe everything in it just by looking at some kind of boundary?
It's not easy, that's for sure. But the idea is that there might be this deep connection between gravity in our three-dimensional universe
Okay.
and a quantum theory that lives on a lower dimensional boundary.
A quantum theory on a lower dimensional boundary. Okay, now you're really losing me.
Think of it like this. Imagine a dictionary
Okay.
that translates between the language of gravity and the language of quantum mechanics.
Okay, so if we could crack this code,
This holographic dictionary.
yeah, this holographic dictionary, we could potentially describe our entire universe just by looking at its boundary.
That's the hope. It would be a huge breakthrough in our understanding of physics.
So let's say we did have this holographic theory.
Okay.
What would it mean for us? Like, what are the implications for our understanding of the world and our place in it?
Well, for starters, it would challenge our most basic notions of space and time.
Like, how so?
If information is truly fundamental, then our perceptions of distance, location, even the flow of time might be illusions.
Illusions.
Yeah, like emergent properties of this underlying information structure.
Wow, that's a lot to process.
Yeah.
Are you saying that everything we see and experience, everything we think and feel, might just be information encoded on some cosmic hard drive?
It's a possibility. We might have to completely rethink what it means for something to be real.
Okay, I'm officially mind blown. But let's back up for a second.
Okay.
If this holographic principle is true, how would we ever know for sure? Is there any way to actually test it?
That's the tricky part. Directly probing the holographic nature of space-time is really tough with our current technology.
So are we just stuck with speculation?
Not necessarily. There are some indirect ways we might be able to find evidence.
Really? Like what kind of evidence would we be looking for?
Well, one possibility is to study the very early universe.
Like right after the Big Bang?
Exactly. The conditions back then were so extreme
Yeah.
that they might have left some subtle imprints on the fabric of space-time.
Imprints that could reveal a holographic structure.
It's a long shot, but it's worth exploring. Another approach is to look for tiny quantum fluctuations in space-time itself.
Quantum fluctuations.
Yeah, basically tiny ripples in the fabric of reality.
And these ripples could tell us something about the holographic principle.
They might. These fluctuations could provide clues about the underlying holographic code if it exists.
So we're like cosmic detectives searching for clues to the biggest mystery of all.
Exactly. The nature of reality itself.
Okay, let's say we do find this evidence.
Right.
Where does the research go from there? What are the next steps in exploring this holographic universe?
Well, one of the big challenges is to develop more sophisticated holographic theories.
More sophisticated.
Yeah, ones that can actually be applied to our universe.
So we need to go beyond this anti-de Sitter space and find ways to incorporate the complexities of our own space-time.
Exactly. We need to upgrade our holographic dictionary, so to speak.
Okay, makes sense. What else?
Another exciting avenue is to explore connections between the holographic principle and other areas of physics.
Like what? What other areas could be connected to this holographic idea?
Well, believe it or not, there might be links to condensed matter physics.
Condensed matter physics. That's the study of, like, metals and semiconductors, right?
Yeah, that's right.
But
It might seem totally unrelated,
it does.
but it turns out that some of the math used to describe holographic theory is also popping up in the study of certain exotic materials.
Really? So it's like the universe is using the same language to describe vastly different things.
It's amazing, isn't it? There might be these deep underlying principles connecting seemingly disparate areas of physics.
And the holographic principle could be the key to unlocking those connections.
That's what we're hoping to find out.
This is all so incredible. It feels like we're on the verge of a whole new understanding of the universe.
It does, doesn't it? The holographic principle has opened up a Pandora's box of possibilities.
And we're just starting to explore them.
Exactly.
But even if we never find definitive proof of a holographic universe,
Yeah,
the journey itself is pretty remarkable, wouldn't you say?
absolutely. It's forced us to think about reality in completely new ways, and that's always a good thing.
So much to think about. I mean, it's almost overwhelming to imagine that we might be living in this giant hologram projected from some higher dimensional reality.
Yeah, it really makes you question everything you thought you knew about the universe.
Totally. And that all the information about our universe, including us, is somehow encoded on this surface that we can't even perceive.
It's like a wild idea.
It really is. So if you had to like sum up the holographic principle for someone who's maybe just tuning in, what would you say are like the key takeaways?
The key takeaways, well, I'd say the most important idea is that information might be way more fundamental than we realize.
More fundamental.
Yeah, like it could be the building block of reality itself,
Oh.
and the way that it's encoded
Yeah.
might actually determine the very structure of our universe.
So it's not just about what the information is, but how it's organized.
Exactly. It's like the blueprint for the universe.
And this encoding happens on this two-dimensional surface,
Right.
the holographic screen,
Yeah.
which somehow contains all the information about our three-dimensional world.
Yeah, it's like saying the blueprints for a skyscraper are more important than the building itself.
I like that analogy. What else?
Another key takeaway is that this holographic principle forces us to rethink our ideas about space and time.
Okay.
If information is really this fundamental thing,
Yeah.
then our perceptions of distance, location, even the flow of time
Hey.
might just be illusions.
Illusion.
Yeah, like emergent properties of this underlying information structure.
Okay, so our perception of reality might not be as straightforward as we think.
It might not be. And finally, I'd say the holographic principle reminds us that we're still at the very beginning of trying to understand the universe.
Yeah, we've only scratched the surface.
We have so much more to learn, and the answers might be far stranger and more wonderful than we can even imagine right now.
It's both exciting and a little bit terrifying to think about all the things we don't know.
It is, but that's what makes science so much fun, right? It's the pursuit of knowledge.
Yeah.
The constant exploration of the unknown.
Absolutely. Well, this deep dive into the holographic principle has been an incredible journey. I've learned so much, and it's definitely given me a whole new perspective on the universe and our place in it.
That's what we were hoping for.
So for our listeners who want to learn more about this,
Yeah.
where would you recommend they start? Are there any good resources out there for someone who's not a physicist?
Absolutely. There are some great books and online resources that can help break down these complex ideas.
Like what? What are some of your favorites?
Well, for a general audience, I'd recommend The Holographic Universe by Michael Talbot.
Okay.
It's a great introduction to the topic, and for those who want to delve a bit deeper into the physics,
Yeah.
Leonard Susskind's lectures on the holographic principle are available online, and they're fantastic.
Perfect. We'll be sure to include links to those resources in the show notes for everyone.
Awesome.
Well, that brings us to the end of our deep dive into the holographic universe. It's been truly mind-expanding. And for all of you listening out there, keep questioning, keep exploring, and never stop looking up at the stars. You never know what amazing discoveries await us in this vast and mysterious cosmos.
Stay curious, everyone.
And keep those brains buzzing.
I would have been on top of the charts, but it's politics. You do some gimmick shit and post, you get a lot of clicks. Drop some real shit and they probably won't acknowledge it.